Okay. Go here, here. Okay. Let's get started. So, a couple announcements. So, number one, I took the at-home spreadsheet off of Teams and sent it via email because what happened was I made a post and I said, don't edit the spreadsheet on Teams. Then somebody edited it on Teams. So I made a reply and I said, don't edit it on Teams. And then after that, somebody edited it on Teams. And so I decided, okay, I don't think Teams was the best way of distributing this. I'm just going to send an email. Because when you edit it on Teams, everybody can see what you put in. And I'm like, that's why I put the download thing there. So, all right, I just took it off and sent it via email. So everybody has that. The bonus homework's open. So in terms of where we're at in the class, we're rocking and rolling for the rest of the semester. I have posted all of the notes, and all of the homeworks are going to automatically turn on. So it's going to be sort of like, and the solutions. So they're automatically going to become visible as well. So it's on autopilot for pretty much the rest of the semester. In terms of what we're talking about, we only have 3 real lectures left because we're going to do 2 lectures on designing discretely braced beams, and we're going to have our final lecture on local buckling, which is something we've kind of been not talking about this whole time, and I think a formal discussion of it's necessary, and that's a way of sort of closing it out. We'll cancel class on Wednesday of next week, and then we'll have our exam through review, and we are done. Sound good? All right. Let's go back and make sure we're all on the same page. So first off, I would hope that everybody by now is comfortable with this. This is the model to determine LTB capacity, right? So what we do is we go into this flow chart with a given unbraced length, and we compare that unbraced length to our 2 anchor points, LP and LR. That tells us what zone we're in, and based on what zone we're in, we have our following computations. The only thing that's not in the flow chart is the CB expression, but that's why I put that up there. Now, let's make sure we're all also cool with this. Everybody look up here. So if we're utilizing table 310, right? So what we do is we divide out the effects of CB, right? And we go into the table with our LB value on the x-axis, the moment on the y-axis, and the moment being the maximum factored moment divided by CB. We find that point, boom, we look up to the right, we find our first solid shape, and that's the section that we try. Everybody okay with that? Okay, let's talk about design then, okay? Because I think if you understand the flow chart and you understand this, then you're good. You can pretty much reason through what you need to do for design. So let's talk about the process, okay? So this process is going to be very akin to what we did for continuously braced beams. There's just more stuff there, okay? So what do? The first thing we need to do is we need to do our structural analysis. So what we're really interested in this step is to achieve 2 values. We're going to need an MU and we're going to need a CB value, okay? Now, we didn't need CB before for continuously braced beams because we were just designing based off the plastic moment. So now we need a CB value. During this phase, I want you to assume a self-weight. I will probably tell you what it is on, for example, on an exam problem because I want us to all sort of be doing the same problem. But in the real world, typically you're assuming somewhere between 50 and 100 pounds per foot. I would say for most routine building design problems, those are pretty common assumptions. And unless otherwise stated, those are pretty good assumptions. Now, what's new also is the computation of CB. Hopefully, this is a case that is reflected in table 3-1. And if it is, just use that value for CB. No need to compute it. But if it's a weird bracing configuration or a weird set of loading, you're going to have to compute CB. It's almost like we needed a homework assignment dedicated just to computing CB. Oh, wait, we did do that. We did that homework 6.4. It's like I planned this stuff out or something. It's kind of crazy. All right. Step 2 is to compute the required moment of inertia. Now, that is the exact same as before. So We take our, let's say, our live load deflection limit of L over 360, set it equal to the max span, solve for IX. So after step 2, you should have the following 3 values. You should have an MU max, a CB, and an IX required. Now, you might also have a maximum shear and whatnot, but again, this is really what you should be yielding after the second step. What you're going to do is you're going to go into table 310. That's the chart where you're finding the point and looking up to the right, and you're going to find the most economical trial section. Now, this only works for that guide if the yield stress is 50 KSI, but for 99% of beams that we design, that's not going to be a problem. And you're going to go into that table with LB and then your MU over CB, okay? And you find a trial shape. What we need to do is we need to check that trial shape to ensure that it has an adequate moment of inertia. And if that's the case, then that's going to be a trial shape that we then analyze. We are then going to analyze that trial section to verify its capacity. Now, with moments, I have a note here. This is very, very important, okay? I would say that unlike continuously braced beam design, this is highly necessary, and I say regardless of beam self-weight. And so let me sort of explain what I mean by that. Let's say I assume a self-weight of 100 pounds per foot, okay? Let's put it here on the screen. So let's say that self-weight is assumed to be 100 pounds per foot. And let's say I do a bunch of math, do a bunch of structural analysis, go into table 310, and I get a W24 by 76. Do I need to go back and update my moments? No. Why? It's already exceeded that. So the idea is that if the self-weight is heavier, if our assumption is heavier than the beam's actual weight, then we don't need to update that assumption. And I would argue for continuously braced beams, you're done at this point. In other words, as long as the beam is heavier with continuously braced beam, or sorry, as long as the assumption is heavier than the beam self-weight, you're good. You know that beam works. For discretely braced beams, that's not the case, okay? You still need to perform the analysis even if this happens for discretely braced beams. And the reason why is because of this. If you have a problem that has a high CB value, you can generate what's called a false positive. And you can get a section that even though it looks like it works, it doesn't. And it will be easier to explain that with an example so that you can kind of see it. But ultimately, the CB value serves to falsely magnify the capacity. And we'll see that later on. Okay, now the shear capacity, for now, you can just look it up. It tends to not be a problem. Later on, we'll talk about how to actually compute shear capacity, but for building beams, it's actually very easy. And then just check the deflection limits. Checking the deflections, it isn't all that mathematically necessary, but I think it's a good idea to make sure you don't have any calculator errors. So, all right. Okay, now a final tip. This is for using table 310. When you're using the table, you might have this happen. So I want everybody to look at this. So if the idea is to do this, right, you might find a scenario where you have a bunch of solid vertical lines that are going up and down. And so it might actually be difficult to figure out which section it is. So I have found that sometimes it may be easier, instead of tracing like this, to just trace upward and find the first section that works. And it is also possible that you find a region, right, you look up and to the right, and the section actually trails off to the next page. You have to flip to the next page and find that point. The pages have some overlap, so you should never have a situation where you have a point and there's not multiple graphs that reference it. Any questions? All right, I think that it is easiest to explain a lot of this with an example. So we're going to look at the following example. All right, so we have a beam that's discretely braced. It is braced only at the ends. We have a dead load and a live load, okay? The dead load shown does not include the beam self-weight. We are going to assume a beam self-weight of 100 pounds per foot, and we're going to design this beam start to finish, okay? And I think you're going to find this is a pretty straightforward approach. But I'll give you all a sec it's a pretty straightforward problem. But I'll give you all a sec to catch up and copy all this down. Again, I think you'll find this is pretty doable. And I hope everybody brought their AISE 15th edition steel construction manual with them. There we go. We got folks getting it out. I like it. Then we got some folks who are like, I don't need to do that. I see how it is. Okay. She's giving me this look. I'm just saying. All right. A couple things I want to write down. What is LB for this beam? Let's just make sure everybody's awake and paying attention. 24 feet, okay? It is 24 feet or 288 inches. We will most likely need both, or we will possibly need both. We'll say that. The length of the beam is also 24 feet. So this is a problem where the length and the unbraced length happen to be the same. They are not always the same value. They just happen to be for this problem because it's only braced at the ends. Now we've been given a dead load of 1 kip per foot and a self weight of 0.1 kip per foot. We're going to say that's assumed. And then we were given the live load of 3 kips per foot. Okay. So what we'll do is we'll say step 1. What I'm going to call step 1 is structural analysis. And specifically what I'm talking about is moment and shear. Okay? So the first thing that I'm going to do is I'm going to handle the dead load. And I'm going to say that M dead is W dead plus W naught L squared over 8. So that's going to be 1.1 kips per foot times 24 feet squared over 8. And that's the moment for the shear. It's W times L over what? If it's WL squared over 8 for the moment, it's WL over what for the shear? 2. Okay, make sure everybody's paying attention. All right. So that is 1.1 24 feet over 2. And let's see, I can probably help you with some of these. So this first one ends up being 79.2 foot kips. And then this one is 13.2 kips. Okay. Now ML is, here, I don't think we need the parentheses there. Okay, so you all help me out with these. I don't want to do everything for you. At some point, I got to get you all helping me out with this. So what's ML? There we go, 216. And then VL. And again, we might have saved ourselves a little bit of time if we had factored the loads and just did WL squared over 8 once and WL over 2 once. but I want you to be in the habit of thinking that you need to do dead load and live load separately. Because again, if there's a beam, let's say, has a point load at midspan, and you think, I know what I'll do. I'll take that point load and I'll turn it into a distributed load, right? Remember, that's the Dr. Mike conceiving he's going to slap my hand method. Don't do that. No. Ow. I'm a dork, I know. Okay, so this is the dead load, this is the live load. So the factored load. So we have MU is 1.2 M dead, 1.6 M live, VU is 1.2 V dead plus 1.6 V live. So what's MU and VU going to be? So 1.2 times the dead plus 1.6 times the live, 1.2 times the dead plus 1.6 times the live. Anybody got an MU value for me?
40.64.
And shear.
93.44.
Boom. Not too bad. Now there's one other thing that we need for this problem, and this is a CB value, okay? We need a CB. Now, here's the problem. We have a simply supported beam. It's got a distributed load on it. And there's a brace here, a brace here, a brace here, a brace here. How many CB values are we going to need to determine for this beam? One. But do we need to do any math? I seem to remember that there was a nifty little table 3-1 that would tell us what is CB for this case. I also seem to remember you all had a homework assignment where you had to derive CB for this case. It's like I wanted you to do that for some reason. What was it? 1.14. All right. Let me stop for a sec. Let everybody get a chance to catch up. I want to see if anybody has any questions on this. On your homework assignment, I actually specifically call out that I'm going to let you use table 3-1 to compute CB, and you'll see what I mean here in a second. That's to make your life easier. All right. Sound good? Okay. Now, before we start going a picking of shapes, we need to compute the required IX. So let's compute our required IX. Now, how do we do that? Okay, we are given a live load deflection limit of L over what? Which is 24 feet over 360, but remember, we want an answer in inches, right? So what is 24 times 12 over 360? Huh? 0.8. Now our live load maximum deflection with a simply supported beam subjected to a uniformly distributed load is, if memory serves, 5 WL to the fourth EI, right? And then don't forget, I'm also going to have a unit conversion in there. But ultimately, all I need to do is swap my I with my limit. So don't forget your 1728. And so when you chug this out, what do you get? You get IX min equals something. All right. Let's let everybody catch up. Here, I'll do that like that so that we can all kind of see everything. But I'll give everybody a sec. I want you to catch up with what we've done so far. All right. Everybody with me? Okay. So now let's get to picking a shape. Okay, so let me show you how this works. So let's select a trial shape. So I want everybody to follow along with me. We're going to do this one step at a time. Okay, so we're going to probably, like for some of you that are skipping ahead, this might seem a little slow, but trust me, there's a reason for this. Okay, so remind me, what was our LB again? 24 feet. And now what we need is an MU over CB. Why are we dividing out CB again? Does anybody remember why? The graph is built based off of a CB value of 1. So what we're going to do is we're going to use 440.64 over 1.14. And what do we get for that? 386.5. That's probably good enough. Okay. So what we're going to do is we're going to go into our guide with these two values. Here's our value on the x-axis. So we'll call this x. This is our value for the y. And remember what we do. We go to our guide, right? We find that point. We look up to the right. We find the first bold section. While you're doing that, let me see if I can help a little bit. Does anybody have a page? I'm just curious.
I got W 18 by 76.
18 by 76. Let's see. So hold on. All right. So well, that's going to take a little while, especially given that I don't have a keyboard. So let's see. Let's use the good keyboard, the one that likes my numbers. So 3-118. So we will break out the snipping tool. So that's the one that we're using. So there's the page, right? I'll make this kind of big so everybody can kind of see it. All right. So just to make sure we're all following, so what we're doing is we're saying, okay, we have a 386.5, which is, I don't know, like 378, 1, 4, something about like that. And then 24, so we're sort of like at that point right there, like that's the point. And so we go up and to the right, and there's the first section that we find, the W18/76. So is everybody okay with that? With finding that? See, this got it isn't that bad, is it? I mean, it's all about once you know how to navigate it, it's really not that bad. So we're going to say try a W18/76. Okay? All right, we're going to try that. Now, I want to look at something. So I want to say check IX requirement. If I remember correctly, this problem has a requirement that our minimum moment of inertia be 965.3 inches to the fourth. So my question is, what is the moment of inertia for a W18/76? What is it? 1330. So 1330, not 130. So my question for you, is this a viable shape, or should we move on and pick another one? So far it works, right? Because the moment of inertia for the shape that we picked is bigger than the requirement. So I'll say this. Section will meet deflection requirements. Now, a note, what would we do if it didn't? Like, what if it didn't meet the deflection requirements? I'm asking you, what would we do? What does that mean, though?
Go to the next line across.
You're saying go to the next line here. I say no. What I would say, abandon table 3-10, use table 3-3 to select. The reason why, here, that box is too big. Let me make that smaller. Here's the reason why I would do that and not do what you said. If this section is not meeting this requirement, what it tells me as a designer is that I am governed by a completely different limit state. Table 3-10 is used to pick sections based off their bending strength. And what this is telling me is that it's not the bending strength that's controlling what section I pick, it's how much it's deforming, right? So I am going to use table 3-3, which organizes shapes based on how well they resist deformation. Does that make sense? So is everybody else okay with that? I think you would result in more iteration doing it this way than this way. That's what I'm getting at. So far, so good? All right, now we're going to do some analysis. Now, let's go back to a couple things. First off, MU, not MU over CB, MU. What was MU? CB is 1.14. We've got VU is, what was VU again? 73.44. These values are based on assumed W naught, which was 100 pounds per foot. What's our actual W naught? 76. Do we need to update these values? Like, do we really need to? No. If this beam can hold up these loads, it can surely hold up its own self-weight. So therefore, no need to update MU and VU. Okay. Now help me out. I need a couple values for the W18 by 76. Okay. Now we're going to get these values from table 3.2. Remember, table 3.2 has got all the money in terms of analysis. Okay. So help me out with something. What's LP and LR equal to? 9.22 and 27.1. What does this tell me? Zone 2. Okay. Note, most discretely braced beam designs will lie in zone 2. Most of them will be zone 2.
In cases like this, how it's not a bold section, would we be better off to move it up, or would that be?
Okay, that's a great question. I'm going to say not necessarily. And the reason why is because we're trying to find the value on the curve, on the LTB curve. And so moving up might not mean that that section works. It might not. In fact, there are many cases where it doesn't, particularly in cases of high CB values. In that range, that was the most economical within that range. Moving up will most likely not work. So Everybody okay with that? Okay. Now, if we're in zone 2, we're going to need some values. We're going to need, CB. We're going to need a phi MP. What is phi MP?
611.
611. Okay. There is a surprisingly potent amount of information baked into this number, 611. And I don't want to get into it now, but suffice it to say that this one number tells me that this section is not a false positive. You're like, we still don't know what that means. You will later, trust me. We're going to need phi BF. What is phi BF? And since we're at it, let's go ahead and write the shear capacity down. What's the shear capacity? Okay. Now, if you're wondering why I'm having you look up these values, is because, as you said, we're in zone 2, and zone 2 tells me that here's our expression, right? I'll just screen clip that one. All right. So here's the expression to compute capacity according to zone 2. And so what do you need? You need a CB, a phi MPX, a phi BF. We already have LP up there. So it's not me just picking random values out of the air. I'm just following the process. So what we'll do is we'll compute this upper expression. So let's do that. Let's do CB phi MP minus that. So this is 611. That's 12.8 kips. This was 24 feet minus, what was L? 9.22. And so what do we get for this? 480.9. Do I have a second on that? So therefore, phi mn is the minimum of CB times all that junk, or phi MP. So that's the minimum of 480.9, or phi MP, which was 611. And so phi mn, 480.9 foot kips. So to summarize, phi mn is 480.9 foot kips, and mu was what? I think mu was 440.64. What does that mean? It works. We have more capacity than we do applied moment. So of course, yeah, this is fine. And if we wanted, we could say our performance ratio for moment is 440.64 over 480.9. And when you chug that out, you get 0.916, which is a pretty strong performance ratio. That's a pretty good design. Now, they don't always end up being that case. Like, they're not always that good. If you want to see the others, so phi Vn was 232. And if we compare that against VU, VU was 73.44. That one's also okay. That one's good. But when you look at its performance ratio, we take 73.44 and divide it by 232. We get a much lower number. It's something like 0.317. Again, steel beams and buildings, they just have a lot of shear capacity. They just do. Now, if you wanted to do a performance ratio for deflection, that one's pretty easy. We just say, okay, the deflection limit is 0.8, and then the maximum deflection is 5WL to the fourth over 384 EI. But now we have the I, right? Because now we're not using some fictitious I, we're actually looking at a given shape. So we just say 3 kips per foot, 24 feet raised to the fourth power. Don't forget our lovely unit conversion. $384, 29,000 KSI. And now we're using 1330. And so when you chug that out, oops, sorry. That should be 0.581, and that obviously works. And you can say your performance ratio is 0.581 over 0.8. And so when you chug that out, you get 0.726. So obviously deflections were important, but for this problem they weren't as important as the moment, right? And we kind of knew that was going to happen when we looked at step 4 and we found deflections, should be fine. So what's the answer to this problem? Use a W18 by 76. Boom. Now, before you all start packing up too much, I got something to show you, but I want to stop and make sure that everybody's clear on this. Did this make sense? Any questions?
Do you want us to do the performance ratio on the test?
You don't have to. I mean, well, let me say this. If I ask for it, yes, but if not, you don't need to worry about it. To me, we're just doing this so that you can see which was the important one for this problem. And in this case, the important one was moment. All right, can I get everybody's attention real quick? All right, so this is for your benefit. This is the homework coming up, and I want to show you, let's see, which one is it? I think is it 6-6? Yeah, okay. So here's the beam that you're looking at, and I want this to make sense. I've structured this problem in a certain way, so I want everybody to pay attention. First off, okay, this first note is really important, okay, because what it's saying is that the self-weight of the beam may be neglected when determining CB. So if I take this self-weight off, the only thing I have is a beam that has 1, 2, 3, 4 braces and has point loads applied at those braces, and it's symmetric. If you look at table 3.1, there is a case that matches this exactly, right? So I'm doing that so that you can use table 3.1 for CB. That's point 1. Here's the second point. How many unbraced segments do we have on this problem? We have 1, 2, 3, right? But really we only have 2. We have the end segment and the middle segment. because this is a symmetric beam. So I want you to think about this problem from a moment diagram perspective. I'm going to have the same moments on this end segment than I am this end segment, right? So what that means is I really need to figure out which one I need to consider for design. This one or this one. Now let's compare the two. All right? Which one's longer, the end or the middle? Middle. Okay? Now let's think about capacity. If the unbraced length gets longer, what happens to the capacity? Goes down, right? All right, that's point one. Point two, which segment, end or middle, has the highest bending moment? The middle, right? It's a simply supported beam with symmetric loads. The max bending is going to be in the middle. Now, which segment has the lower CB value, the end or the middle? The middle, right? Because the middle is going to have the gradient's not going to be very high. So from a design perspective, the middle segment versus the end segment, which one do you actually need to consider for the purposes of design? See my point? So, you can check the end segments, but I guarantee you they're not going to govern. So you only need to consider the middle segment for the purposes of design. Now, what we're going to talk about next time, because it's not going to happen on this assignment, but what we are going to talk about next time is what happens when you have false positives. Again, we haven't explained what that means. We will on Friday. That's all I've got. I will see you all on Friday. And
On table 3-1, for that case,